Hello friends, in the last lecture we have discussed about the isothermal process wherein the temperature remains constant and the other state variables change. And now in today's lecture we are going to discuss about the isobaric process. The isobaric process is a thermodynamic process in which the pressure of the system remains constant. That is, P is equal to constant, therefore the change in pressure is 0. Now we are considering the system as a cylinder having a massless, frictionless and movable piston, and the cylinder is filled with an ideal gas. Now, since the pressure is constant, the initial state of the system is the volume of the gas is Vi and the temperature of the gas is Ti, and the state changes, the state of the system changes, and the final volume is Vf and the final temperature is Tf. Now, since the pressure remaining constant, now here in this case we know that the pressure of the system in the isobaric process is always constant. Hence, the change in pressure is 0. Now, the system accepts heat from the surrounding. So, its temperature changes and hence the change in temperature is not 0. Now, we know that as the temperature changes, on the temperature depends the internal energy of the system. Now, since the temperature changes, hence the internal energy of the system also changes accordingly. Now, so delta U is also not equal to 0 since delta T is not equal to 0. Because delta U is the internal energy of the system which changes as temperature changes. Now, Q is not equal to 0, that is the system is accepting heat. Now, this heat which is accepted by the system, work is done by the system in increasing the volume, and hence W is also not equal to 0. Now, according to the first law of the thermodynamics, we know that Q is equal to delta U plus W. In the isobaric process, the system receives heat. The internal energy of the system changes. Work is done by the system, and hence the energy is used for both change in internal energy and for doing the work. The work done by the system can be found out by the formula W is equal to PdV. Now, here is the PV diagram for the isobaric process. That is, on the y-axis we are considering the pressure and on the x-axis we are considering the volume. Now, we know that in the isobaric process the pressure does not change. Hence, the pressure Pi is remaining constant, it remaining same. And the volume of the system is changing from Vi to Vf. This line AB indicates where the pressure is same. Now, we know that in the isothermal process where the temperature remains constant, at that there the graph of the PV diagram of the isothermal process is called as isotherm. Similarly, the PV diagram for the isobaric process is called as isobar. Now, this line connects all the points where the pressure remaining constant. Now, here the graph is a straight line because the pressure at all these points are same, but the maps which are provided by the meteorological department where the pressure at the points which are remaining constant, where the pressure remains constant, the maps are called as isobars, and they are not straight line but they are curves. They are the points which are joined. The constant the points which are at same pressure, they are joined. They are not straight line, they are curves. So, this is the representation of the isobar. Now, we would be discussing the thermodynamics of the isobaric process. Now here delta P is equal to 0 because pressure is equal to constant. The initial volume and the initial temperature of the system of the ideal gas is Vi and Ti, and the system changes to Vf and Tf, which is the final volume and the final temperature of the system because the pressure is remaining constant. The work done in expansion of the gas from Vi to Vf is W is, we know that W is equal to PdV. Now, since here the pressure is constant, so W is equal to P change in volume, that is Vf minus Vi. Now, why we can write this in such easy way and not in the isothermal process? In the isothermal process, we are considering the integration of PdV. Why? Because the pressure is changing. The volume is changing, but the pressure is also changing. The temperature remaining constant. For constant pressure, we are considering dW. Then again the pressure changes, and for again constant pressure, we are considering dW, and all such dW we are adding in the isothermal process. But here, since the pressure is not changing, we can consider directly P because the pressure is constant, Vf minus Vi. Now, according to ideal gas equation, we have PV is equal to nRT. Now, since pressure is constant and the volume is changing from Vi to Vf, so the volume is changing from Vi to Vf, then N, the number of moles of the gas inside the system or inside the cylinder, is remaining constant because once the system is fixed, the number of moles of gas are also fixed. So N remaining constant, R, which is the universal gas constant, is a constant. Now there is a change in the temperature from Ti to Tf. So the temperature changes from Ti to Tf. So this equation we can write like, so this equation, let this be equation 1 and this be equation 2. So from 1 and 2 we can write W is equal to P Vf minus Vi, we can write N R Tf minus Ti. Let this be equation 3. Discussed in the initial lectures the change in the internal energy, which is change in internal energy delta U is given by N CV delta T. This delta U is the change in internal energy, N is the number of moles, CV is the specific heat at constant volume, and delta T is the change in temperature. So the change in internal energy is given by delta U is N CV Tf minus Ti. So let this be equation 4. Now, according to the first law of thermodynamics, according to first law of thermodynamics, we have Q is equal to delta U plus W. So we can, from 3 and 4, we can put up here Q is equal to delta U. Q is equal to delta U, which I can write N CV Tf minus Ti plus W, which is N R Tf minus Ti. Now, Tf and Ti we can take in common. Here we have N and Tf minus Ti and N and Tf minus Ti. So N and Tf minus Ti we can take in common. So Q is equal to N into Tf minus Ti. So this whole we take in common. So here remains CV plus R. Now since we know Cp minus Cv is equal to R, or Cp is equal to Cv plus R. So this Cv plus R is equal to Cp, we can put up here. So we get Q is equal to N. For this Cv plus R, I will write Cp. So I write here Cp into Tf minus Ti. So this will be equation number 5. Now in the isobaric process, we have found that the heat received is used to increase the temperature, and that is Tf minus Ti is the increase in temperature, and how much temperature will be increasing depends upon N, that is the number of moles, and Cp, that is the specific heat at constant pressure for the ideal gas. And the heat received by the gas is used for increasing the internal, partly it is used for increasing the internal energy, and partly it is used to do the work. So this is the thermodynamics of the isobaric process. The next thermodynamic process which we are going to consider is the isochoric process. So isochoric process is a constant volume process. It is a thermodynamic process in which the volume of the system remains constant. So the volume remains constant, so the change in volume is zero, is the isochoric process. Now the heating of a gas in a constant volume container is an example of the isochoric process. The system does no work on its environment during the isochoric process. Now, in this isochoric process, the volume is constant, hence the change in volume is zero. Now we know that work done is PdV. So, pressure into the change in volume, but the change in volume is zero. So, the work done in this process is zero. The work done is zero. Now, since in this isochoric process, the system is receiving heat, then hence Q is not equal to 0 because it is receiving heat. Its temperature is changing, or increasing. Its internal energy will also be increasing. So delta T is not equal to 0, delta U is not equal to 0, and Q not equal to 0 in this isochoric process. Now, this is the PV diagram of the isochoric process. On the y-axis is the pressure and on the x-axis is the volume. Now Vi is the volume of the gas, initial and final. Pi and Pf are the initial and the final pressures. Now the straight line shows the points that the volume remaining, the points where the volume remains constant. So this is the PV diagram of the isochoric process. So according to the thermodynamics of the isochoric process, we know that delta V is equal to 0 because change in volume is 0. Now we know that work done is P delta V or PdV. Now since delta V is 0, P into delta V is 0. So work done in the isochoric process is 0. Now, according to the first law of thermodynamics, we have Q is equal to delta U plus W. Now, W equal to 0 be 1, and this from the first law of thermodynamics be 2. Now, the change in internal energy delta U is given by N Cv dt according to what we have discussed in our earlier lectures. So, let this be equation 3. So, from 1, 2 and 3, putting the values in equation 2 from equation 1 and 3 we get Q is equal to delta U is N Cv dt plus W is 0. So Q is equal to NCV dt. So the system does no work at all, and all the energy which is supplied to the system is converted into its internal energy, the internal energy of the system. So this is the thermodynamics of the isochoric process. Thank you.